Good morning, everyone. Today I'll be presenting to you our thesis project, which is about implementing reactive collision avoidance using evolutionary neural network. Our advisors are Dr. Mohamed Shalan and engineer Hesham Eraqi. The team is Aya, Mariam, Melissa, Heba, and me. First of all, I'll guide you through our agenda. We will start by talking about the problem domain and then the project description. And we will then talk about our outcome. The project has three main outcomes: the simulation outcome, the model optimization outcome, and the hardware outcome. And then we'll talk about the future work. Okay. So we were in the problem domain. As I mentioned, there are 5 levels of autonomous vehicles. We talked about the first level. It's a driver assistance level. It only has one autonomous functionality, such as park assist or cruise control or brake boost. The second level is the partial automation. The driver still takes control of all the functionalities of the vehicle. However, the driver can basically disengage from some functionality such as lane centering and pilot and pilot assist and auto braking. Those features are there to help the user disengage from, for example, having to keep in the lane or for example responding, but the user still has to have their both hand on the steering wheel all the time. Okay. The third level is the conditional automation, and it's said to be the eyes of vehicle, because the user is theoretically allowed to or able to engage in other activities besides driving, because the vehicle is supposedly kind of autonomous in perfect conditions. However, those perfect conditions are not available. It needs, for example, a very defined road lanes, very defined road signs that are not very available in most of the countries. So those vehicles are not widespread. The fourth one is the high automation vehicles. It has most of the functionalities. It can accelerate and perform steering and braking. And also monitors the road conditions. It takes decisions of changing lanes and taking different paths. However, this doesn't perform very well in extreme conditions, extreme weather conditions such as snow or rain or mud. It still needed the user intervention in this situation. The final one is the full automation. The fully autonomous vehicles should be autonomous under all conditions. They shouldn't require the user's intervention at any point. They need a lot of artificial intelligence and a lot of data to be able to build such a logic, and there's not many of them because of this problem of extreme conditions that I talked about earlier. The common factor in all those autonomous levels is collision avoidance. Starting from the first level that does beeping whenever there is a nearby obstacle, up to the last one that fully monitors the road and takes the paths, collision avoidance is there, and collision avoidance is a preventive measure that prevents collision. And it should be it's a real-time application, should take immediate actions if there is a probability for collision. It should predict all collision scenarios. It shouldn't be customized for a specific collision. It should be general to all scenarios, so it should be generalizable, and it's a safety critical application, of course, so it needs to be very high in performance. So this is our domain. Next, Mariam will talk to you about our problem definition.
So I'll be talking about our project description. Our thesis problem is that we need to find a collision avoidance method that optimizes the trade-offs between complexity, generalizability, and performance, as Mariam mentioned. After doing our research, we found different variations of models that work on these problems with different trade-offs. Complex solutions such as deep neural networks were found to be very high in performance. However, it's very hard to generalize for most of the problems. So after searching, we found a very high potential in a research that uses a mixture of genetic algorithms with a neural network. So we decided to do a research project about this algorithms and algorithm and its possible optimizations. So why evolutionary neural networks? The reason for the choice of the genetic algorithms with the neural networks is that genetic algorithms mimic the natural selection process of the survival of the fittest, which is in this problem will let the best solutions survive until the end of the algorithm. And of course, such a complex problem as collision avoidance has several external features with very complex function representations, which calls for having a neural networks. So concerning our research methodology. Our solution, in our solution, we are building on an existing machine learning model that uses genetic algorithms. And we did changes and optimizations in the model, which Melissa will be talking about shortly. And our main project strategy is to train the model on simulation, and then do transfer learning to the model after it being well trained to the ROM. So our main project outcomes are the optimized model, the simulation, the hardware, and finally the research paper, which is the main thesis outcome. And then Melissa will be talking about the project, the model optimizations.
To optimize our model, we found many aspects that can be made to reach the ideal solution quicker and more effectively. The first aspect is the selection method in the genetic algorithm. It is the most important element as it ensures that the best chromosomes have the high probability in being selected. Accordingly, the algorithm will derive to the best solution. For the selection itself, there is 3 methods that can be used. The first one, in the tournament selection, a number of candidates chosen randomly from the existing generation in a genetic algorithm is selected as a parent, and then the selected candidate is passed on to the next generation. This process is repeated as often as the candidate was be chosen. This selection is the most commonly used, in spite of the fact that it has a very high complexity. In the truncation selection, the candidates are organized by fitness. Only the best candidates are chosen as parents. It's used for a big population because it derives to the best solution fast. The starting point is the parameter of the truncation selection. It signals the proportion of the population to be chosen as parents and takes extending from 50% to 10%. So we chose the truncation selection for our project as it optimized our model from ON squared to ON log n for complexity. In the stochastic selection, we select potentially useful solution for a combination. So it wasn't the best choice for our project. Secondly, the activation function in the neural network. The activation function decides whether a neuron should be activated or not by calculating the weighted sum and adding bias with it. The purpose of the activation function is to introduce nonlinearity into the output of a neuron. This is needed because in neural network, data activation function is just a linear regression model. The activation function does the nonlinear transformation to the input so it can learn and perform complex tasks. The main activation function in the neural network is the sigmoid function. However, the sigmoid function causes the vanishing gradient problem. So we choose the tangential function as an activation function in our model because its value lie between -1 to 1. So the output is zero-centered, which makes training and optimization easier. And now Heba will be talking about the simulation.
So why would we need to use a simulation in the first place? So as my colleagues have just mentioned, in order to train our genetic algorithms, we will need to test its performance over and over again using different generations of chromosomes and save the ones that give us the best performance and navigate through the environment without collision. Such process can be inefficient and time-consuming and can harm the hardware. All these limitations can be eliminated by using the simulation. Simulating the model. Next slide. Simulating the model and the environment help us maintain a higher efficiency where there's no need to move the vehicle around physically, and it is less time consuming where simulation can be left to train the model without human interference, unlike in the real life setup. It is easier to train the model in different and customizable environments. The simulation also helps us avoid the hardware damage during the initial training process, and helps us to avoid hardware susceptible inaccuracies, since we can have the simulation start from the exact starting point after each iteration. Previous work in this area involves training the model on a MATLAB simulation shown. However, this 2D simulation is not very realistic and does not simulate the real-world environment in the best manner. So we worked on improving this simulation using Gazebo, which is a simulation environment that supports the robot operating system known as ROS. Gazebo helps us customize our vehicle, sensors, and environment. It also helps us to add the real environmental factors that might affect the environment, such as the physics of the environment, with factors such as gravity and mass. However, Gazebo comes with its own drawbacks. These are mainly having a complicated environment to set up, where although it gives us many options to add to our training environment, the process can be tedious and overwhelming, which also means it's tricky to debug. Having these many options also means that we need the high computational power to visualize the simulation, as well as being limited to the Linux operating system, which is the only operating system that supports ROS. Adding to all this, due to its complexity, Gazebo is not often well known to many developers, so it was challenging for us to get started with it without having any background or experts in the field to guide us when we get stuck. This also applies to the online community, where there aren't many tutorials or blogs that we're able to refer to, which is usually not the case in other common frameworks. Next, Aya will walk you through our hardware setup and our results.
So I'll be briefly taking you through our progress in the hardware. As we said, the last phase of our project was to migrate our model on the hardware. So we were trying to mimic our simulation. So the platform we chose was the iRobot Roomba, as it has a low cost that's available and an open platform for development with many features built in. The sensor we used was the RP LiDAR A3 LiDAR sensor, or the laser range scanner, for its availability and low cost. And to communicate between those two components and allow the model to execute, we use the Jetson TXT SoC for its availability and high performance. And to tie all these components together, we wrote some scripts to interface with the different hardware components. As mentioned before, to train the model, we migrated the chromosomes between different platforms to help speed up the learning process in an indoor environment. And that was between the MATLAB and Gazebo to the hardware. So we'll now play the demo video. sharing some of our results. In the previous works, the model used to take up to 8 generations and around 132 seconds in perfect conditions. In Gazebo, however, the model takes around 15 generations and around 120 seconds to train. The environment we replicated was kind of related to the actual environment we were training in, and how, since we were limited with the space we were training in, we ended up using simpler environments than we first intended to. And the velocity was in relation to the actual hardware velocity. The hardware with the model would take up to 7 seconds until the first collision without transfer learning. And after transfer learning, it takes around 17 seconds until the first collision. Moving on, since this is a research project, there's room for continuous improvement in research. Some areas we suggest are training and modifying our project to work in an outdoor environment, as well as train in various environments, and apply to different applications that use navigation systems such as wheelchairs, robots in factories, or autonomous vehicles. Thank you very much. Are there any questions?